human beings are very late comers to the skies. And although we might think that we're now pretty good at it, the natural world, with the help of several million years of evolution, has produced a dazzling range of aeronauts whose talents are far beyond ours.
The story of how animals managed to colonize the air is truly astonishing. First into the skies were insects. They initially had 2 pairs of wings, which in due course were modified in many different ways. But after having had the skies to themselves for about 100 million years, a new group of animals took to the air. Vertebrates, creatures with backbones. They faced a different challenge, for their bodies were much bigger and heavier. But eventually they evolved several ways of solving that problem. We will travel the globe to trace the details of the extraordinary skills of the black-boned flyers. This is Borneo. And here there are still great tracts of pristine rainforest. Forest that is wonderfully rich in animals of all kinds. I am being winched up into one of the tallest trees here, in search of a creature that can give us a hint of how backboned animals first took to the air.
Hidden among these leaves of this fern, high up here in the canopy, is a very remarkable little frog. It's a harlequin tree frog, and it's a very, very good climber. It spends most of its life up here clambering around in the branches. Here, it's away from the numerous predators there are that might attack it down on the forest floor. But if in fact a predator were able to get up here to hunt it, a snake perhaps, well, the tree frog has a remarkable trick for defense.
It glides. It has membranes between greatly elongated toes, so that each foot becomes a parachute which slows the frog's descent and so enables it to make a relatively safe landing. The vertebrates made their first forays into the air around 260 million years ago. And it's very likely that some of these pioneers used skinny membranes to control their falls in much the same way as this little frog does.
It has to be said that it's not a very good aerial navigator. It seems as though it just jumps and hopes for the best. But there are animals up here that glide around from tree to tree, which are very good navigators indeed, so good in fact that they can go from one tree to another and never go down to the ground in their entire lives.
One of them is a little lizard called Draco. Each male has his own little territory in the branches and tries to attract females and warn off rivals by flashing his dewlap. He also spreads coloured flaps of skin from his flanks that, when fully extended, do more or less the same thing. But there are predators among the branches. Snakes also live up here, and they hunt lizards. But Draco's side flaps now serve another purpose. He uses them to glide by hitching forward his specially elongated ribs. And he is so skilled in the air that he can steer and land on the trunk of his choice.
So, if you live up in the branches, it's less laborious and indeed safer to travel by air than to come down to the ground. But if you want to be a true flyer, you have to be able to fly not only downwards, but upwards. You have to have powered flight. This is another reptile, and one with even greater flying abilities than that little gliding lizard. Today, sadly, it's extinct.
This is Dimorphodon. We can deduce from its fossils that it had the muscles needed to beat its wings. And computer imagery can show us what it must have looked like.
Dimorphodon was one of the first large animals ever to travel by air 200 million years ago. It belonged to a group called the pterosaurs, the winged reptiles.
It was probably a forest dweller and a descendant of a tree-living glider. This gliding ancestor might have had wings like those of Draco's that were made of skin and perhaps extended from its fingers down to its ankles. But pterosaurs had evolved larger wings with a hugely elongated fourth finger. The wing membrane was strengthened internally by thin rods of a stiffer tissue. There were muscle fibers too, that enabled it to modify its contours as it flew. Looking at the wings in section reveals the secret of their efficiency. They have a rounded front edge and a sharp back edge, a shape known as an aerofoil. It works by forcing the air flowing above the wing to speed up. This faster air has a lower pressure, and the wing is sucked upwards. The larger the surface area of the wing, the greater lift it can produce. So it seems certain that pterosaurs were very competent flyers. And judging from their teeth, it seems likely that many fed on the great variety of insects that had preceded them into the air. Insects had had the skies to themselves for around 100 million years. Now, bigger creatures had arrived, reptiles. The pterosaur design for flight proved hugely successful. They used their new powers to spread beyond the forests and colonize whole new environments. A great number of them lived and fed near water. We know this because fossils of many species occur in rocks that were once mud at the bottom of lakes and shallow seas.
This one shows the skeleton of an animal that 150 million years ago fell to the bottom of a shallow lagoon. This is its head. Here's its backbone and tail, hind legs, and here, stretching from these long extended finger bones, are its wings. And this fossil is particularly remarkable because it shows an impression of the membrane in extraordinary detail. You can see every little tiny fold. You can judge how an animal lived by its skull. And this one had these long jaws with forward-pointing teeth. And we think that that indicates that it lived by skimming across the surface of the lagoon and snatching up fish which impaled on those teeth. This very different one, it's just the head. As you can see, it has very long jaws, and at the tip of the lower one is this little tuft of very fine filaments. And we know from other specimens that those filaments originally stretched right along the length of the jaw.
This bristly fringe enabled the creature to filter feed, taking in a beak full of water, expelling it through the bristles with the beak half closed, and then swallowing what the bristles retained.
And here is a skull of a very much bigger species from Brazil. And it had neither teeth nor bristles in its jaws. But microscopic examination of the surface of the bone here reveals very tiny little blood vessels, and that suggests that these jaws were once covered with a horny beak. So that maybe this animal used its beak like a pair of forceps to pick up small little reptiles or maybe catch dragonflies in the air. And this particular skull reveals something else about the life style of this specimen, because at the back of the skull it has this great flange. And pterosaur skeletons from other species have been found, some with such flanges, but others without. So it's thought that maybe this was the difference between the sexes. Maybe it was the male that had these big flanges at the back which had displayed them, and maybe it was covered with skin. We can only guess.
Many different pterosaur species evolved these head crests, and it seems very likely that they were coloured. This spectacular example is known as Tapejara, and it made its home beside inland lakes. But pterosaurs diversified in other ways too. Some evolved much larger bodies. This species had a wingspan of over 20 feet, 7 meters. But not all pterosaurs lived in the forests or near water. An open, arid landscape like this one was the likely home of one of the most extraordinary.
Around 70 million years ago, a pterosaur appeared that was of truly colossal proportions.
That was one of the largest creatures that has ever flown. It was the size of a small aeroplane, and it was called Quetzalcoatlus.
Its immense wingspan allowed it to ride on the currents of warm air that rise up from sun-heated land. It could then glide great distances searching for food. Small creatures like lizards, or the dead bodies of much larger ones, dinosaurs.
But the pterosaurs, with their wings of toughened skin, weren't the only group of reptiles to make it into those ancient skies. About 150 million years ago, another reptilian group appeared on the planet that also flew.
Like most reptiles, including pterosaurs, these creatures began their lives inside an egg. But they had evolved a revolutionary new design for flight, one that would usher in a remarkable fresh chapter in our story. And unlike the pterosaurs, they're still with us today. They are, of course, the birds. Some today can provide clues about how their ancestors managed to get into the air. This is the chick of a bird found in farmyards everywhere. A bantam hen.
And at this very early stage in its life, it can show us something very interesting about the origin of that crucial piece of flying equipment, a feather. Its feathers are downy. That's to say, they're made up of simple filaments. And their function is not for flight, but insulation, to keep this little creature warm. And back in the Jurassic period, long before the arrival of true birds, very similar looking feathers appeared on very different animals, reptiles, dinosaurs, to be precise.
To find evidence for that astonishing statement, which not so long ago was highly controversial, we're heading for China. Northeast of China's Great Wall, near the borders of Mongolia, lies the chilly province of Liaoning. Here, there are great areas of rocks that were laid down as mud in the bottom of immense freshwater lakes. The bodies of animals that were swept down into these lakes were slowly entombed by the fine-grained sediment that preserved them entire and in exquisite detail. And from these rocks have come specimens that solve one of the most hotly debated of evolutionary arguments, the origin of the birds. The key specimens are now in Beijing, where they've been delicately prepared under the microscope. They have been studied here by one of the world's greatest dinosaur experts, Professor Xing Shu. First, he showed me one of his older specimens, part of a dinosaur's arm. But thanks to the fineness of the mud of those ancient lakes, there is more here than just bones.
You see here? This species is called a reptiles. So reptiles is an animal like 2 or 3 meters long, so quite a big animal. And here's the arm, hand. You see here dark filamental structures.
Yes.
Along the arms and hand. Actually, primitive feathers. And those feathers are very simple, very, very simple. So we believe they represent the very primitive stages for feather evolution.
These simple strands were made of the same material as the feathers of today's birds. They were relatively thick and must have been quite stiff, so they would have stuck out beyond the dinosaur's arm. Behind them were shorter strands that covered its whole body. Like the down on the chick, these might have kept the dinosaur warm. But those longer strands most likely had a different function. Clues to what that might have been can be found on an even more extraordinary fossil. These claws and finger bones belong to a creature called Caudipteryx. The long dark shapes around them are the remains of feathers. The single strands are here rather more complex. They had barbs, thin filaments, attached to either side of a central rod. This looks more like a bird's feather. Caudipteryx had around 26 of them along each arm. This may look like a wing, but the feathers were not very long. And when you compare them to the size of this creature's body and its long legs, it's clear that they weren't big enough to enable Caudipteryx to fly. So what were these feathers for? Microscopic examination has revealed that they were colored and patterned. So maybe they were used for display, perhaps to wave around during courtship to attract a mate. But then it seems that they also helped the dinosaur in a different way. We can find a hint of how they might have done this by watching the way some young birds use their first feathers today. These are 10-day-old pheasant chicks. Their feathers are not yet fully developed. At this stage, they're similar in structure to the feathers on that dinosaur, Caudipteryx, and grow in a line along each arm in much the same way. But these early feathers are also too short to enable these creatures to fly. Nevertheless, they're very helpful. Pheasant chicks hatch in nests on the ground, but they soon need to roost high up where they'll be safe from predators. Flapping these simple wings gives the chicks a little extra lift to help them climb into a tree. And when the time comes to return to the ground, those first feathers again are a help. They don't provide a large air-catching surface, but they're enough to slow a chick's fall and make that landing just a little softer. Maybe the feathers that had initially kept the dinosaurs warm now also helped them to get into the air. And then, only a few years ago, the mudstones of Liaoning produced yet another extraordinary fossil. It's been named Microraptor, and it's clearly a small dinosaur. But this specimen is particularly exciting because of its feathers. Feathers on the forearms there, feathers on its hind limbs, and even feathers right at the end of its very long tail. But there's something that makes these feathers different from any other feathers we've seen on dinosaurs before. They are narrower on one side of the quill than on the other, just like bird feathers. Microscopic structures within them suggest that they had flashes of iridescence. So these feathers were probably used for display. But their asymmetric shape is characteristic of flight feathers. The air flowing over the narrow front of the feather can produce lift. So, could this strange-looking dinosaur, with feathers all over it, actually fly? Some people think that those feathers on its hind legs would have made it rather difficult for it to walk around on the ground, and that it would have been more at home climbing. And those claws on the fingers and toes were obviously very helpful in climbing up tree trunks. But those aerodynamically shaped feathers certainly suggest that its arms were being used as wings. This four-winged dinosaur must have been a really extraordinary animal. Its front wings were broad enough to enable it to glide, and its muscles on the chest were sufficiently strong to enable it to flap every now and then and help it on its way. But the wings on the hind legs were probably not held spread out, but kept beneath the body to help the animal to steer. Now, clearly, these dinosaurs were on their way to join the pterosaurs in the sky. And then, discovered once again in the rocks of China, came creatures that are recognizable as birds. This is Confuciusornis. There are two of them here. They no longer have heavy, bony jaws studded with teeth. Instead, they have short beaks made of horn without teeth, lightweight. And the tail is no longer supported by a whole chain of small bones. Those bones have been reduced to this tiny little stump here. These are true birds. But the long feathers attached to the tail of one of these specimens can reveal something intriguing about these early birds. To find out what they were for, we can look for a bird here in Borneo that has very similar tail feathers. This is the racket-tailed drongo. and its tail feathers bear an astonishing resemblance to those of its distant ancestor, Confucius ornis. They don't seem to help its flight in any way. So the drongo must be using them for something else. Display. And so, while the birds continued to improve their flight, they also continued to use their feathers in courtship, as their dinosaur ancestors had probably done.
The birds use not just the shape of their feathers for display, but also their colour. And there's some really lovely examples of that here in Borneo.
These birds are colourful enough, but one is particularly spectacular. This is the Bornean peacock pheasant. This is the male. His feathers are emblazoned with colourful iridescent patterns. And that's because they're used to attract the attention of a female. Her feathers are comparatively drab. First, the male lures the female into his courtship arena with the promise of food, a worm. He begins to shake his magnificent feathers. He clears the ground of anything that might interfere with his performance. As the female dives in after the worm, he raises all of his feathers in a huge fan. If she approves of his display, she may choose him as a mate over other rival males. Eventually, she makes off with the offering of food, and it seems she was not as impressed as she might have been.
So feathers, so lightweight and so easily erected, can serve as billboards on which to advertise for a mate or warn off rivals.
But to see how the early birds used their feathers to achieve fully powered flight, we are returning to Britain. Here on a loch in Scotland, we can watch some of the most majestic flyers around today. Whooper swans. These particular birds were in contact with human beings from the very first moment that they hatched, so they allow me to get really close to them. The small feathers on their bodies are still essential for keeping their owners warm. But this one is a wing feather.
It's extremely strong, but very light, and the filaments on either side of the quill, the barbs, zip together to form a continuous surface which is strong enough to hold the air. But if the air is to support a big bird as it flies, it has to move over the wing very fast. And in order for that to happen, these swans will move at speed across the surface of the water, like an aircraft taxiing before takeoff.
when you're close up to a flying bird like this, you can see what a wonderful piece of complex engineering their wings are, able to change their shape and their beat to respond to every little change in the currents of the air around them, and so propel them forward and lift them upwards. Oh.
So, how do birds' wings actually work? If we slow them down, we can watch in detail the many subtle changes they make as they move up and down. The feathers overlap to form a smooth, contoured surface that extends far beyond the bones within. With a curved leading edge at the front and a sharp trailing edge at the back, they have the classic aerodynamic shape that produces lift. They are aerofoils.
With each downward beat, the air pressure above is reduced so that the bird is sucked upwards.
Wings like these, consisting of jointed bones covered with closely fitting feathers, can make very subtle, delicate movements.
The feathers slide over one another so that when the wing changes shape, there is no loss of smoothness and the contour.
When the swan slightly retracts its wings in between beats, the sliding feathers ensure that the aerofoil still produces lift. As well as lightweight beaks and shortened tails, some of the bones of its body have become hollow. The result is an extremely efficient, lightweight flyer.
We're traveling around 30 miles an hour now, and yet these birds could easily accelerate and leave us behind if they wanted to.
So feathers, since their first appearance on the bodies of dinosaurs, have acquired several different functions. Initially, they served to keep their owners warm. Then, some grew large and acquired colour and were probably used in courtship displays. And only then, after millions of years, were they used to help their owners get into the air. So around 150 million years ago, birds joined the pterosaurs and insects in the skies.
Then, around 66 million years ago, came the global catastrophe that triggered the disappearance of a vast proportion of the animal life of this planet.
An asteroid hitting the Earth was the most likely cause of this mass extinction. In the devastation that followed, the dominant creatures of that age, the dinosaurs disappeared. The pterosaurs were completely wiped out, and only a few of the birds survived. The skies, for a short period, must have been relatively empty. But then a new kind of flying animal appeared.
Now was the chance for a group of furry, warm-blooded little creatures that had been scampering around the feet of the dinosaurs for several million years. They were the mammals.
The first of them to take to the air were doubtless gliders. And one mysterious creature still alive today can give us an idea of what they were like. It lives in the rainforests of Borneo, and it's called the kubong. It has an enormous blanket of furry skin that stretches from the side of its head right down to the very tip of its tail. But to see how it travels through the air, we must wait until nightfall. As soon as it lands, it regains the height it's inevitably lost by clambering up the trunk. It's by far the most skillful of the forest gliders and can travel over 100 meters in one leap. It's undoubtedly a very ancient animal, and some believe that it may well have survived virtually unchanged from that time long ago when mammals first took to the skies as gliders. But soon the mammals did better than that.
This is a fossil that dates from about 52.5 million years ago. Here's its head with very well-developed teeth, backbone and ribs, and long tail, hind legs, and most important of all, from our point of view, hands with enormously elongated fingers. And there was skin between those fingers. These were wings, and they could flap. This is the earliest fossil yet discovered of a bat.
We have no evidence to show exactly how bats' fingers first began to lengthen to support their wings. But we can understand how those early bats flew by looking at their modern descendants. These are some of the largest. They're so big that they're often called flying foxes. And they have a wingspan of over a meter.
When you slow a bat's flight down like this, you can see that its four fingers are spread wide on the downstroke, keeping the membrane wide and taut, and then clumped together on the upstroke, with just the thumb at the top free. Boy.
This folding of the wings reduces the bat's air resistance between each beat. To maximize the size of its wing, the back edge of the wing membrane is attached to the ankles. Bats roost by hanging upside down. And this is how they tend to spend their days.
It's thought that the first mammals were nocturnal. That doubtless was the best thing to be, out of the way of the dinosaurs that were rampaging around during the day.
So the bats continued the nocturnal habit of their ancestors. And they had also inherited the acute senses needed to move around at night. Eyes specially adapted to operating well in low light, and an acute sense of smell that enables them to find food in the dark. In any case, birds already dominated the daytime skies. With their wings of skin and nocturnal senses, the bats became a huge global success. Today, there are over 1,100 species of them. That's over a fifth of all mammals. So, by 50 million years ago, 3 groups of large backboned animals had joined the insects in the air. The pioneers were reptiles, pterosaurs, with membranes of skin stretched from elongated fingers. Then came a group of dinosaurs that acquired feathers and became birds. But when the pterosaurs and dinosaurs were swept away in a global extinction event, the stage was set for the birds and the newly emerged bats between them to take command of the skies.
Each of these 2 groups had evolved its own techniques for getting into the air, and each was destined to bring their skills to astonishing extremes.
Next time, we see how birds adapted and diversified to become the remarkable creatures we see in our skies today. Lethal hunters. Formation flyers. And aerial acrobats. We explore how the bats developed a new super sense that enabled them to hunt in the pitch blackness of the night. And we visit one spectacular place where the battle for the skies between insects, bats, and birds still continues.